What? You like 10? I don't get started, yeah. I don't feel respond.
So, good morning. And one more homework before we turn. Notice that homework 8 is due on the same day as the exam. If you are if you have limited time, then you have the liberty to submit it a little late. At least that is 24 hours. I don't tell you exactly how much time that is, so that you submit it on time. So there's at least 24 hours of buffer time in there. Any general comments or questions? Yes, please.
I'm a little bit curious about your YouTube, like that you have like assets turned on.
Assets, what is that?
It's like where you make money from like ads on the videos.
No, that is that's unintentional. Sorry.
Okay.
I would be the last person to do that. So I should go and. So how do you turn that off? Maybe you could tell me after class.
I don't know. I did not.
Because it is true. I mean, I found Alex right here. I found Alex's YouTube good enough that I don't think it is. I don't know how much appropriate it is, but I went and subscribed to Alex. So I think it's okay. But they were nice. So I guess you noticed that. So tell me how to remove that, but you said you don't know. Yeah, so I'll try to work on it. And,
It's not good. I just thought it was funny.
oh no, I don't like that. I wouldn't like it to be there. Put it like that. So,
You might honestly get them to use me. I make money.
the number of clicks, even with 50 students I have here, is probably like for a lecture video. I think you get 2 clicks, maybe 3 clicks. During the exam, maybe it goes up all the way to 20, 24. That's it. It doesn't increase after that. And remember, these are all private videos, so that's different. Yeah. So not private really. There are 3 of them, right? Private, public, and what's the third one? Yeah, unlisted. Yeah. So these are mostly unlisted videos, so it doesn't. Yeah. But there is, I mean, since you guys pointed out, there is another channel I maintain. So there is a small center I started back in my home country. So that channel is something I promote in the sense that that is for kids in the who do not have these kind of facilities. So I do give lectures every Saturday there. So it's an online feature. But it's again, it's not for money. It's completely free, but look it up if you want. This is not part of the course. This doesn't give you anything, but if you want, it's called Fix Science Center. This came up, just look it up. It should be self-explanatory, that's all. And I should also say that it is not, it started last summer. And I expected that there will be a lot of people who will be interested, students, if it is completely free and you make it. Just you come and do hands-on projects there. But pretty much there is zero audience. So I just go there and lecture pretty much to my friends. I have 3 or 4 friends that I lecture and it gets recorded.
Keep doing it.
So the idea is that, yeah, keep pushing on it and hopefully it will get somewhere. We didn't do any marketing, that was something. But, yeah, okay. Sorry about the distractions. Blame it on Alex, we brought it up.
What from your advertising?
Huh?
Advertising, like, spread the word, I don't know.
No, I don't think,
Social media.
okay, I'll take 2 more minutes, I should not go beyond. I think the main point, it's like our courses, like it is easy to say that, oh, this is the best. Like advertisement is about telling something that is not the correct feature, right? You're exaggerating. But that I feel is cheating.
Yeah.
Right? So it's like saying there is a similar version here, 206A. There is a course there. So it is easy for me to come and advertise that, oh, that's the best part. And if you do that, you will get this. But that's not what it is. So it's better to be appropriate. And otherwise, eventually in the long run, you won't be able to keep it. I think that's my belief, I guess, belief of philosophy. Yeah. But yeah, let's those are our lifestyle methods, which I'm not. My method might be wrong. So let me talk about physics. This might be slightly better. So, okay. Any other comments on subject related things other than? Yes.
The midterm is over 6, 7, and 8.
Yes, 6. Yeah, so midterm exam is on notice that it is including 6, which we covered in midterm 2 also. If you notice on the web page, I moved that section a bit to on afterwards, so it should be very clear. Usually I break that in a way so that that part of the section is what you have to concentrate on. So 6, even though it was covered in midterm 2, I felt most of you did not have a clear picture of it. So we have homework 6 again on midterm 3, 7, and 8 is what we studied in the last few weeks. Again, that's a good point to mention it. 6, 7, and 8. 6 is there in midterm 3. Any other comments? Okay. This point is a good point in the course in the sense that we have covered the idea of electric field, anything related to electricity, broadly called electricity, and we have covered the concepts related to magnetism. So these are 2 completely independent topics, especially when you see it as an effect in daily life. One is related to magnets and one is related to electric wires. You don't expect them to have any relation, but the way we brought it up, you already see a connection that a moving charge acts like a current, and current is the source of magnetic field. So there's already a connection that a moving charge and a charge are the different sources. But now what we are going to do is how electric field can create a magnetic field and how a magnetic field can create an electric field. Here, particularly this week, we'll be talking about how a change in magnetic field can create an electric field. This is how most of the power that we use is generated. Even though you might realize that, oh, there is coal, there is nuclear power, water, hydroelectric, all those are good, but eventually all those are used to move something. And that motion happens in a magnetic field. And that motion leads to voltage. So how do you generate voltage? Eventually, it is typically you move something in a magnetic field, and that generates a potential difference which you can use. So that's what we want to talk about here. It's broadly called Faraday's law of induction. Just say Faraday induction. And this law of induction. And I pointed this before. Faraday discovered this somewhere around 1810 or so, and that was significant enough that it was no less than the digital revolution that we are going through today. That was a big realization, and it led to so many ideas that it led to significant amount of technology being developed based on this. So we pay close attention to this. You should be able to connect with something that's happening around you. So let's do a very quick review of what we have done: electric field, charges, magnetic field, moving charges, and so on. So if you have a charge, the review, the charge is Q. In principle, we talk about two charges, but in between we have been introducing the idea of electric field. Anywhere there is a charge that creates an electric field. And once you have created an electric field, that means you have created a potential difference. This electric field exerts a force on something else, but let's think of this as a potential difference. And we will call that V. So charge creates electric field, which is the analog of force per unit charge. And once you've created a force is nothing but a manifestation of the fact that is differences in energy between 2 points in space. A higher point in space has higher gravitational potential energy, lower point with respect to the ground has lower gravitational potential energy. Once you've created this difference in gravitational potential energy, there's a tendency for massive objects to go from higher to lower gravitational potential energy. Similarly, the moment you have kept a charge anywhere close by, that creates an electric field that's equivalent to the electric gravitational force. This is the electric force. But more importantly, you have created an electric potential difference. Like the high and low point in gravitational energy, there is a potential difference you have created. That means if you put another charge in there, it will try to go towards the lower potential. So that's the basic idea that we have been building on. The details are there for precision if you want, but broadly the idea is only that much. The same thing goes with magnetism. We have moving charge now. Which is Q times V. Or we also said a moving charge is equivalent to a current. So we will also say this is current carrying wire plus I times VL. So that's a small tiny stretch of wire if you want. A moving charge creates a magnetic field. And magnetic field also has so notice this is the energy associated with the force, right? Magnetic field is an analog of the force, or it exerts a force, and there will be a magnetic potential difference here. So this is electric potential difference, magnetic potential difference. But most of the time, magnetic field is perpendicular to the force that is exerted, and due to that reason, for our purposes, it is sufficient to say that magnetic field that never does work on a moving charge. So if there is a charge, it does not exert or doesn't give any energy to it. So due to that reason, it can only change the direction of the path of the particle, but it doesn't actually help it gain any kinetic energy. So we would like to connect these things now. We completely saw it independently, but now let's connect these two together. Let me particularly talk about the magnetic field. This is also useful for your exam. So it is kind of a simple summary of homework 6 and homework 7. If you have a current carrying wire, it creates a magnetic field. And how you find the magnetic field is hold the wire such that hold the wire with your right hand, such that the thumb is pointing in the direction of the current, and the curl of the finger gives you the magnetic field. It is circular, so that's the magnetic field. It's going in circle, and now the way I'm going to represent this is the two-dimensional plane. Everywhere on the right, this is going into the field. So that's the part of the circle where you go in, and on this side you will come out. This goes in, comes out. Notice they are going further, the density is going down, and that just represents that it is weaker as you go far. That's your magnetic field due to a wire, and it is good to point out that it is equal to mu naught over 4 pi, and it is 2 times the current I over how far you are. How far you are, that's the distance, that's your observation point. That's the distance R. That's the distance R. This distance is always perpendicular to the wire, so that you're talking about the shortest distance to the wire. In principle, this wire could be of any shape. For our purposes, as far as understanding goes, let's always think of this as a straight, infinitely long wire, so that this expression is relatively straightforward. If it is not straight, if it is circular, or if it's a finite wire, this expression gets more complicated in the sense that the length of the wire that comes in can be a 1. Left side is a vector, right side doesn't seem to be doing the vector sign. To introduce that, you have to point out that this is circular. So the fact that it's circular is given by this symbol. This means it is tangential to a circle that is in the plane perpendicular to the wire. If you take a wire that is a plane that is perpendicular to the wire, draw a circle on that, and this is the tangent vector to that circle. But for our purposes, it just means that the magnetic field lines are circular. That's just a symbol for that. So if you have a wire, you create a magnetic field. And now we can talk about, once you have a magnetic field, what happens to another wire in the magnetic field, or a charge, moving charge, right? A moving charge or a current carrying wire, they behave very similarly. So now let's talk about what happens to a charge in this magnetic field. So let me define this magnetic field. And now we have a charge positive charge that's moving, let us say, horizontally, or let's say, vertically. This is your velocity. The current carrying wire produced a magnetic field which is circular around it. You bring in a moving charge close to that wire, and if it is moving, now you have to use your right hand rule. So we already used the right hand rule, but that was involving the thumb and the curl of the finger. That's typically called the right hand rule number 2, but both have the same ideas. And this is using right hand rule number 1, and that is have your 4 fingers pointing in the direction of the velocity in such a way that your palm is facing the magnetic field, and when you open the thumb, that gives you the direction of the force. So the force is to the left when you're looking at the board. So that's the force. And if you remember circular motion, velocity is tangential in circular motion, and acceleration is towards the center. So if there is a force to the left, that means acceleration is to the left. So this leads to circular motion, and this will start going in circles. That's the effect that we are interested in. Again, a current carrying wire, or for that matter, a moving charge creates a magnetic field. That magnetic field exerts a force on another moving charge or current carrying wire, and if it's a charge, it makes it move in circles. That's the simple concept we have as of now. And now we are wondering, or the point is, can we be clever and make this charge move in such a way that it creates a potential difference? Creating a voltage is like saying you create a battery. Can you make this charge move in such a way that you can effectively create a battery? That means all the positive charges go on one side, all the negative charges go on one side. So that if you can achieve that, you've pretty much created a battery. And the idea is, can we create a battery in that sense? So this is the basic idea again. This is how you would create a battery. Let's have a magnetic field. The magnetic field is easy to generate. You don't even have to generate it. Already you have the magnetic field. We are all immersed in a magnetic field of about 10⁻⁻⁴ Tesla. Right? 10⁻⁻⁴ doesn't mean that it is small, it just means in what units you are in. If you're talking in terms of Gauss, it is 1 Gauss. So there is a magnetic field all around us. And now let's say there is a positive charge, right? We already said that if you have a positive charge, if I hold on to a positive charge, let's say there is a metallic sphere that is charged on it, and I run with it. I want to build a battery, so I literally take a metallic sphere, and it has a charge on it, and I run with about 1 meters per second. That's very easy for me to do. Like I don't even have to really run. A brisk walk might give me 1 meters per second. And the idea is, can I build a battery like that? And I'm going to demonstrate that you can really build a battery like that. And after that, it's just a matter of being clever. Instead of running, you want to do something else so that you really don't get tired of that. So that's going to be the basic idea. So if there is a positive charge, and if I run with it, I already told you that there is a force to the left here, but since I'm going to the right, I'm going to fingers in the direction of V, magnetic field facing the palm, and the palm or the thumb for giving you the force. So that's your force. Right? So that means this positive charge will get drifted to the top. That's good. Now let me have a negative charge also. If I have a negative charge also, so that so that's the drift, let's say, that's the force on the positive charge. What about the negative charge? What will be the force exerted on the negative charge? Anyone? The positive charge experiences a force on the positive side. Negative charge, for instance, it is going to be downward, so you just have to flip the sign. So that's the force in experience, right? So a positive and a negative charge experience force in different directions. So that already gives you an idea. You have a positive and negative charge. In a magnetic field, it experiences a field for moving away. And that means that positive will go that side, negative will come this side. That's a battery in essence. But where are these batteries? So now what you do is let's where are these positive and negative charges? That's basically a conductor. So think of a conductor. What is an electric conductor? It is an infinite source of positive and negative charges. There are free charges that are available and they will move if there is a force on them. So an electric conductor has a lot of positive charges, lot of negative charges. So if you run with a simple metallic wire in a magnetic field, so I'm just talking about this is a conducting wire, copper wire. That's a conducting wire. Hold on to this and run at 1 meters per second. All the positive charges come here. Let me show this as. That's your velocity v. So I'm having a simple conductor and running with it. All the positive charges move upward and all the negative charges move downward. That's a battery. And if you were to touch this, you should get an electric shock. But we always walk with electric wires around us, but it seems like we do not get electric shocks. So is this really true or not? But it is really true. It's just that it is really small. How small is this? Let's calculate how much voltage can you generate this way. So I'm saying that I have collected charges here. Positive and negative charges. So higher potential, positive charges are higher electric potential, negative charges are lower electric potential. So that is, if I have to connect a wire, there will be a current passing through it. But how much is the voltage? Is it even good enough? If it is in nanovolts or something, that's not good enough. So let's calculate this. How much will this be, or how much will the voltage be? So what is the equilibrium here? Once there are enough positive charges, a new positive charge will not like to go there because this positive charge will get repelled from here and negative charge will get repelled from here. So there is a balance here, and that's given by the electric field or the electric force canceling the magnetic force. So eventually, at equilibrium, this positive charge gets repelled by this, so that's Q times E, electric field when it's created by the positive and negative charges, and V is Q times V times V, how fast we are going and the magnetic field. But we are interested in the voltage. Electric field, I refer to the electric field, but electric field is equivalent to voltage. Once you create an electric field, you have created a voltage. Remember, energy per unit length is a force. So voltage per unit length will be your electric field. So this will be Q times voltage. When there are two V's showing up, there is capital V, that means voltage, and that's velocity. Let's start writing this as small. Same V, that's a small V and one is the capital. Q cancels out and then V over L. Over L, where L is the length of this wire. Q cancels out and the voltage or the potential difference I have created just by running with a metallic wire in my hand is related to velocity, magnetic field, and the length of the wires. Let's see how much voltage can you build out of this. Let's make it very simple. We can of course make run very fast. We can put the wire on a car and do it. For the matter, car itself is a metallic object. So when you're moving, you're actually providing such a phenomena. But let's say you're just making it 1 meter. So that's a minimal you can do. And we will make it extreme field again. Magnetic field is 1.0 into 10 raised to -4 Tesla. It's slightly smaller, probably 0.5 times 10 raised to -4 Tesla. And length, let us say it's about 1 meter. It's possible to run with a one meter wire, and you immediately see that that's about 10 raised to -4 volt. That is 0.0001 volt. The amount of voltage you need to have your phones functioning is at least 3 to 10 volts, let's say 10 volts, and that's significantly small. Let's see how much can you cross. So let's now do a faster version. So let's say you're driving on the interstate, or you can actually go faster by using mechanical devices. But let's say you're just thinking of 100 miles per hour, so that's about 50 meters per second. So the extreme version now is V is 50 meters per second. Magnetic field, let's say we create one of the largest magnetic fields. That's about 1 Tesla. So that's 1 Tesla. And the length again, let's say 1 meter. And suddenly you say that, oh, that's 50 volts. I've noticed just by changing the configuration, it is possible to create very high voltages, but this requires high technology. Like the MRI machine that you see, if you have gone in as a huge apparatus, you cannot afford to have so much of apparatus just to build your battery. So that might be economically not feasible. So you want to get clever, and that's exactly what we will see, and that's exactly what people did in 1810 when we talk about there was a revolution like that. They came up with clever ideas to build these technologies, and it became very easy for to have power available for everyone. So that's broadly the idea. But now let's make it. How can you make this at least relatively easier to do? So let's do this again, but this time. So again, let's have a magnetic field. And you still want to have, so this is pretty much a battery now. Any metallic wire that is moving creates potential difference, or for that matter, acts like a battery. So we want to connect it to a circuit. So this is how you can do that. So you have two rails, and that's your metallic wire. That's your metallic wire or connecting wire. If the wire was on its own, you would collect these positive and negative charges that acts like a battery, but now the moment you have connected these to this rails, it starts connecting that electricity. So now that positive charges are not bound to stay on top, so now they will start moving. And so there is positive charges here, there is negative charges here, there is a tendency for that. But there is the positive charge will try to come to the negative charge, and you suddenly have a current carrying wire now without a battery. Appreciate this, that there is no battery connected to this. Just by moving this rod, you can generate a current, or here we will call it, you can induce a current. That's Faraday's law of induction, that by making something move in a magnetic field, and we will come to the fact that what exactly is the principle behind this, we will see that it is the flux of the magnetic field that is important. But the basic idea is that the motion, usually that's important, dynamics can generate a current. Here, there is a resistance R, and now let's again talk in terms of how can we visualize this, or how can we interpret this as what exactly is happening? Is it just the velocity, or is it a deeper principle that is coming in? Is it just the velocity that can generate a voltage, or is it something else? As I pointed out just a minute back, it is going to be the flux of magnetic field. See that? Let me rewrite this equation. So we have a voltage which is V times B, which is the magnetic field, and there is a length L. So the voltage, which is equal to current times resistance, right? Using the standard Kirchhoff's law. There is a potential difference between 2 points. You complete the circuit through those 2 points, and you get current times resistance in that segment of the circuit is equal to the potential drop. We said this is equal to the velocity times the magnetic field. Let me write it other way. So that's magnetic field times the length times the velocity with which you are moving. That's your velocity. Let's change this a little bit. Velocity is nothing but how much x changes, right? So if you just want x, velocity is change in x with respect to time, horizontal distance with respect to time. So let me write that as v times L delta x over delta t. Notice in this particular scenario, magnetic field is a constant and the length is also a constant. So I can put this L and V in that change and interpret this as change in V times length times x. So the length here times x over the change in time. The length times x is the area that is going to play an important role in this analysis. It is the area that forms a loop that decides how much magnetic field is going through that loop. And that will be a concept we will introduce here, which will be called the flux of the magnetic field. So this is area. So it is B times A. So we are going to say that this is equal to the change in flux of the magnetic field divided by time. At what rate is the flux changing? So to define what is magnetic flux, magnetic flux. Phi subscript B, that means phi stands for flux and B is magnetic flux. This is magnetic field dotted with the area. I'm making this simple, pretending that magnetic field and area is a flat surface. It doesn't have to be. Then you integrate over tiny elements. So that's your flux. In more detail, this will be magnetic field dotted with the A. That is magnetic field is constant, then the same amount, and that's just the area. So this is the area element. Remember, this will be equal to B times A times cosine of the angle between these two vectors. Area is a vector, and the direction of area is always perpendicular to the vector. So it is normal to the vector. Okay. So that's your flux. And what is happening here is that how much voltage is generated is decided by how much flux is passing through this area. If you were to increase this area, the flux is increasing and the voltage, there will be a voltage generated as to how much is the rate of that increase. And that is all that is important. Before I go and make this introduce Faraday's law, I should say that this mechanism is how almost all power sources use. The basic idea is that something has to move. This seems very unrealistic in the sense eventually this is a rail, how far can you go? Maybe at the most of 1 kilometer, that's not a realistic system. So what you do is you somehow want to make this circular, right? This is a linear system, so that doesn't help you, you cannot keep going, but you get clever and you rotate it. That's basically a motor or a dynamo. Like you make this a rotational system, have the magnetic field in the same direction, but you make this rotate itself. And that basically is how you create power. And how do you rotate it? You make the water come and fall onto that, and that's a simple rotation. So a very simple system where water comes and makes things rotate, and you put a magnetic field in it, and you have created a power source. And that's what most of the dams do. Sometimes if you don't have hydroelectric power, you make this rotation happen by burning coal or using nuclear power. Either way, eventually you make something rotate so that it generates the electricity that is needed. Let me make this more precise so that we can realize that it is not necessarily the area that is important. We can also make the angle that can change. So we want to make this into a law. We have already motivated that it is probably the flux, the rate at which the flux is changing that decides how much voltage is created. So this is the idea of Faraday's law of induction. Is the topic today. So Faraday's law of induction pretty much says the same as what we said there. The induced voltage, that's the induced voltage is equal to, as a minus sign, minus means that the system will always oppose whatever you try to do, and it is equal to the rate at which the flux is changing. That's magnetic flux. Magnetic flux is how much magnetic field is going through a loop of wire. you have to first create a loop, notice this as a loop, right? There is a possibility that current can run through that loop. And if you can change the flux, if you just keep a magnetic field that is not sufficient, you have to somehow change the flux inside that loop. Here we were very simplistic, we change the area. And if you want to have more magnetic field, you create a bigger area, right? So that is what we did. But now that we know that it's a rate at which flux changes, you don't have to really change the area. Instead, you can change the magnetic field itself. That's one possibility. And in fact, the best part, which is the clever part, is that you don't have to neither change the magnetic field nor the area. Instead, you can rotate this and you get the angle that's coming in here. You can change the angle here. And that's the best way of doing that. And that is how most of the power plants generate electricity. So we will talk about those things. Let's first introduce the idea of the magnetic field, or before that, the negative sign here. This says that system, by system I mean the electric circuit or Faraday's law. System tries to oppose what we are trying to do. Trying to achieve maybe. We are trying to generate more voltage and the system will try to oppose that. That fact, if we try to increase the area, the system will try to decrease the area, or broadly speaking, it will try to decrease the flux that is going through. So that's very briefly. Let's talk about magnetic flux, which I introduced that. We have already talked about electric flux. So we are now talking the same concept, but with the context of same idea there. Let me describe. So let's say that it's a magnetic field. And the flux passing through an area A will be described by, so this is, let's say, a sheet of paper. So this could be, this has an area A, and I'm keeping it like this here so that you see only a cross-section, not that this line represents an area. So this is a surface with area A. If I have such an area, let me ask a question. So if I have such an area, what's the direction of this area? Is area a vector or a scalar? Is area a vector or a scalar? Anyone? Typically, we do think of it as a scalar, but it also has a direction. If you think of my palm as having an area, yes, that is length times breadth. We always talk about this might be 5 centimeter by 10 centimeters square. So that's about 50 centimeters square. That's how we say it is a number. But that it also has a direction, a unique direction, and that is that perpendicular to that surface. So area is a vector. The 50 centimeters square that I just mentioned, that's the magnitude associated with that vector. The direction is perpendicular to that surface. So always area vector is normal to the surface. So here, when I say this is an area, I'm saying there is a normal vector to that. If it is completely flat, it is not clear whether the normal vector is towards the right or to the left. But typically, you can think of the area as a closed surface and it is outward to the normal. So if it is, for example, a sphere, and you have a tiny area here, then it is in the outward. So when the inside and an outside, so it is always in the outward direction. Here, let us choose it to be the right side, so that's your magnetic field, and that's your area vector A. So that's a possibility, and then what's the flux passing through that area? So this is the dot product coming into picture. So the flux for that particular area is B dotted with A. That's equal to B times A, the magnitude of B, magnitude of A times the cosine of the angle between these two vectors. Magnetic field is pointing to the right. Area vector, notice area is my palm here. Area vector is perpendicular to that. It is along the direction of the magnetic field. The angle between them is 0. And cosine of 0 is 1. So this is the maximum it can get. And that's the idea that if you want to collect, so for example, because of the flow of water and you want to collect something, you will always keep it perpendicular to that flow, correct? So if you want to collect, let us say, you want water to get into a bucket, the face of the bucket, you will always keep it perpendicular to the flow. And that's the basic idea that flux, right? Flux is how much magnetic field passes through this area. If you want it to be a maximum, you want it normal to the magnetic field. What if it was parallel? Now this is the same surface again. So that's the surface, but now I keep it here. And again, I can ask how much magnetic field passes through this area A. We again calculate, nicely speaking or intuitively speaking, we would say nothing is crossing this area, so it should be 0. And we will see that it will come out to be 0. What is the area vector now? The area vector is perpendicular to that, so that's your area vector. That's your surface. Let me draw that like this. The surface. And B is still in the right direction. So phi B this time is B dotted with A. That's B times A times cosine of the angle between magnetic field, which is still in this direction. That's 90 degrees. So that's cosine of 90, and cosine of 90 is 0. So flux, again, intuitively, the field you want to have is how much magnetic field is passing through the surface. If you simply imagine this as a flow of water, you want to keep it perpendicular to that flow. Magnetic field is a flow of an entity, which we say is the magnetic field, right? So that's the flux. But what Faraday says is that it is not the flux that is important. We want to change this flux. If you can change this flux, the rate of change of flux creates the magnetic field. And you see that there are 3 quantities here: magnetic field, area, and the angle between the magnetic field and the area vector. And those are the 3 things you can change. And based on those 3 ideas, you can have at least 3 independent ways of creating voltage. Change the magnetic field, that's one way. Change the area, that's the second way. And the third is change the angle between the magnetic field and the area. That's the third way. Or you can have a linear combination of any of this. You can have all these 3 things happening together, and that's good enough. And we will go by one after the other and see how this is generated. So let's begin by bringing out all of these 3 factors together. We write that down. So the voltage generated, induced voltage, is minus of the rate of change of flux in a magnetic field, which is equal to what we are seeing just now is the flux is equal to B times A times cosine of the angle between the magnetic field vector and the area vector. Each of this could depend on time. I could have a uniform magnetic field and then there is no time dependence. But if I have a time dependence, this derivative will act on the time dependence. I could have the area vector change with time, which is what we did in the previous example. And I could have angle change with time. But if I just take this as a mathematical equation, I have three functions which are functions of time. So let me do that distribution. I have rate of change of magnetic field. Excuse me. I can have a magnetic field change with time and have these two remain the same. Distributed, have the derivative property come in, minus of magnetic field remains the same. Area changes with time. Distribution of the derivative, and I could also have B times A times d by dt of cosine theta. In principle, all three could be contributing, but typically what we do is that in a system, either the magnetic field is changing, or the area is changing, or the angle between the area and the magnetic field is changing. And those are the three independent ways of generating voltage. So this will be magnetic field changing. You can have area changing, or here it is the orientation that is changing. And notice that it is necessary that something has to change. Just because you have a lot of flux is not sufficient. You have to change the flux to be able to generate current. So to demonstrate that, let me have a simple example which also shows up in your homework. Where you will try to change the area, but then you will notice that it's not always in the same the same rate that you have. So let me bring that out. So let's have a hypothetical situation where the magnetic field is confined to a region. Typically, it is difficult to confine magnetic field to a strict region, but let's say we could achieve that. This means that magnetic field is zero beyond this line. That is, it's uniform magnetic field inside this box region. Right, that is a B from here. And let's have a simple loop of wire. No battery connected to that. Right, that's your R. And if you simply connect your phone to a wire, it is not going to get charged, right? You need a battery for that. This is not going to charge your cell phone, so the resistance R could be your cell phone. That's not going to charge, so that's useless. But then you say that, oh, I was told that I can change the area and I can generate a battery. So what you do is that you move this in So all the while you're outside this magnetic field, you ask how much is the flux going through this area? That's your loop. And you're asking how much is the flux of magnetic field going through this? No flux, it is not going to travel. But now, as you enter the magnetic field, now the flux is changing. So the flux is this one. And as you move to the right, this flux is increasing. Area increases, amount of magnetic field that is going through this loop is increasing as you're going in. And so this generates a magnetic field and there is a current that goes in this loop. What's the direction of the current? We'll come back to that. But there is surely a current that goes through this loop. So that is an effective battery. Effective battery here. And associated current. So your cell phone is getting charged in this situation. But let's keep going in to push yourself in. And as I said here, that every time you try to do something, the system will try to oppose you. That means to say that you will literally feel it. If you were trying to go in, the system will try to push you out, and you will do some experiments in the lab where you will really be able to feel this. You will be able to feel that it is actually pushing you out. But once you get in, so if you had enough energy that you pushed it in, and now you're in this region, and you would think that there is a lot of magnetic field here, right? So there is a lot of magnetic field and a lot of flux, but it does not create, and it does not act like a battery because the flux is not changing. Flux has to change. This is constant now. There's a lot of flux there, but when you move from here to there, the flux has not changed. So no voltage. So no voltage here. So your system or your iPhone will not get charged, or your phone will not get charged. Right? No battery. Move this further down, it comes here. And now you're actually decreasing your flux. Again, you might think that you're decreasing your flux, that doesn't help, but that's okay, because as far as you're changing flux, that's good enough. Whether it is positive or negative, it doesn't matter. What will happen here is that this now acts like a negative battery. That means that it is here, if it was going in this direction, here the current will go in the opposite direction. So it is like you have changed the polarity of your battery. So effective battery is there. Effective battery current goes in the opposite direction. And once you have gone down here, there is no current. And that should give you a simple idea of how this works. But now we want to be more precise. Now, what we will do next time is make all this more precise, and we will be able to talk about what exactly is the direction of the current. So maybe let me make a question mark here. What's the direction of the current? Is this correct? You'll analyze, is it going to be clockwise or counterclockwise? In what direction is the current going to be? And how much is the current going to be? Based on what is the velocity, what's the magnetic field, and what's exactly the area that is changing. We will be able to talk about how much exactly is going to be the induced current. I'll stop here. Thank you.